When will the exam be final grade?
Hopefully by Friday. Can y'all see your partial point grades?
Yes, but you have to like press. It's hard.
You mean see the grade without partial?
Yeah, without partial credit, you like go to the exam two, then you click on this, and then you launch the activity.
And then it shows you what your grade is.
Yes.
Okay, I didn't know if y'all could still see that or not. Because I made it inactive, but I didn't know what that really meant. Oh, there's no need for that. We don't need to be on video. So the question was asked, we're all ladies on Zoom. Ladies, the question was asked, when is partial credit grades going to be finalized? And it'll probably be Friday. That's my goal. Okay. Okay. Are you kidding me? Go away. It's in lab, but yes. Okay, ladies, I don't have the big TV screen on for Zoom. Y'all are just on my laptop, which means I can't see you anymore. Can one of you unmute and tell me if you can see just the slide, if you like what you see? Is it good?
We can see the slide.
Were we good?
Yes.
Okay, great. Thank you. Y'all were muted on my computer. Is Josh physically coming? Is he like literally almost at the door?
Probably not.
That sounds like a lot of issues. Okay. So, infrared spectroscopy, and some of you, I think, actually did the lab. Some of you did not do the lab. If after this you want to go and kind of see what our IR looks like, then you can always stop by the office if the door's closed and I can show you. You can look at it, whatever. I don't mind opening it for you. It's really hard to mess up this instrument, so I feel good about y'all getting comfortable with it, okay? So we need to know how to use the IR, but we also need to know how to interpret the spectrum, okay? And basically, we're going to learn about several different types of spectroscopy over this semester and next semester. We're going to learn about nuclear magnetic spectroscopy next semester, which is kind of fun, like a puzzle. But all this spectroscopy has to deal with how different light, and light is that loose definition of the electromagnetic spectrum, light interacts with matter, okay, and different ways. Oh, much closer than I thought. So basically, for the IR spectroscopy, we're taking advantage of the light in the infrared section of that electromagnetic spectrum, okay? And some of this is like lecture slides. So there's lots of contemplative questions. We don't have to always stop and discuss those. Here's our reminder about what the electromagnetic spectrum looks like in case you have kindly squirreled that away. Of course, IR is over on the right-hand side. I don't know where my mouse is. Helps if you're touching the mouse. It's over here on the right-hand side where we do have longer wavelengths, okay? So IR is kind of this second type of spectroscopy here. We have NMR as well, and then we will try to work in a little bit about UV vis when we get to a chapter that talks about conjugated double bonds next semester. Part of the reason I want to make sure we touch on that is because ACS does periodically have a question about it. And it's an easy concept, so it's not anything that's very difficult. You can see over here on the other side of the table, the information that's obtained. NMR literally tells us what our structures look like. Okay, once you get halfway decent at it, you can piece together where your hydrogens are and where your carbons are. Your UV Vis, which we'll talk about next semester as well, tells you if there's a conjugated pi system. So a double bond, a single bond, a double bond, that kind of stuff. Is that present? And even how many of these bonds are there conjugated together? Okay. What we're talking about tonight, IR spectroscopy, tells you more about the functional groups. And that's certainly how we use it for our purposes. You can get more information out of it than just that. Some people can actually fully identify their structures with IR, or at least identify whether they've made the right product depending upon software. We're looking at just functional groups. Okay, so we know that matter can exist like electrons in kind of particle and wave-like nature, okay? What we have to think about for IR spectroscopy is the wave-like nature of our matter. So the samples that we're looking at specifically, okay? So what that means for us is that bottom bullet point, okay? Our molecules that we're analyzing via IR spectroscopy are going to have rotations and vibrations and movement similar to the things that we had learned about when y'all talked about quantum mechanics with Dr. Bradshaw, okay? Stretching, rotating, uneven rocking and all this kind of stuff. But they're only going to do these things at specific energies. So different functional groups have these capabilities at discrete energies that are different from one another, okay? So each of these different bond types will do stretching or vibration or rotation at a certain energy levels. So basically we're using the IR to cause an excitement in these bonds, and then we can of course watch what happens, how the molecule reacts as it goes from an excited state, and those bonds go from kind of an excited state into a lower energy state. That's what we're doing, okay? So basically that's the second point. If the photon of light is hitting the molecule, it's going to interact with that molecule, and we can observe it, that molecular vibration that's being caused by this light interaction, okay? Let's see. Typically, IR, those wavelengths, will cause some kind of molecular vibration as opposed to translation, rotation, that kind of stuff. So here's kind of a reminder of the various types of bond motions that we can do, or that your molecules can exist. We have stretching, where it's literally stretching the bond in between the two atoms that are in that covalent bond. You have something called in-plane bending, which you can think of as kind of a scissoring movement, and then you have out-of-plane bending vibration. So the last two are vibrations, which is what we see. And while those two things both seem, they're both vibrations, you can actually get specific information out, and different functional groups that have the in-plane bending have a certain readout in the IR spectrum versus the out-of-plane bending. Like that actually gives different numbers and can help you identify specific conditions for your functional groups. Typically, we don't worry too much about that, but you'll see tables that actually have these specifications, and that's why they have those specifications. Okay. So here's kind of a reminder about how you probably heard about IR in the past, okay? Your night goggles, night vision, can detect infrared. Obviously, we can't really see it with our eyes. And then you have thermal imaging and things like cancer detection, all of that good stuff. Some of the stuff that's like super, super theory heavy, I'm trying to not dwell so long on it so we don't, go to sleep. All right, so the IR energy the IR light has energy. Certain types of bonds require different amounts of energies in order to excite them and to cause vibrations. And so here we're seeing the carbon-hydrogen bond versus the carbon-oxygen. We've got these energy gaps, okay? And you can see that the carbon-hydrogen bond has a bigger energy gap between these two states, the lower energy and the higher energy, versus the carbon-oxygen. So we need more energy in order to excite a carbon-hydrogen bond for vibration versus a carbon-oxygen bond. And that also means that when the bond is going back down to its lower state, it is releasing a different amount of energy. So that can get picked up and interpreted by a detector. Okay. So the entire part of the IR light spectrum is what a sample gets hit with. So it's not with a specific wavelength of light, it's the variety of IR wavelengths. There are some instruments that you can tune to specific wavelengths. That's more what we do with UV vis. But for IR, you're hitting it with a broad wavelength variation so that you can kind of hit all these different energies, okay? So your different waves that have frequencies, these different frequencies are going to be absorbed by the sample, and that will give us differing energy levels based on the vibrations for those functional groups, for those bonds involved in the functional groups, okay? So some of the things in this chapter, for instance, this thing called salt plates, that's how samples used to be made. And in fact, our IR can actually still do that, but we have found money to find a very splendid instrument. And we, those of you that went to lab know, we can just put our solid samples on top of the IR, and perhaps you've even watched the procedure video. We don't have to do a lot to our samples anymore to analyze them via IR. It used to be quite painful making the salt plates. If it cracked, because you blended your compound up with a salt, you pressed it down really, really tightly, lots of pressure, and then you had to put it in a holder. And if the holder caused the plate to crack, you had to go back and do it again and again and again. They used salts. Why do we think they maybe use salts? That's fine. We don't have to answer. Salts aren't covalent bonds, right? So there's not really rotations and vibrations and that kind of stuff. So that's why we would use salts. Okay. Really, they said salt plate. We still called it that. But a lot of times you use KBr, potassium bromide. It's super cheap and people aren't tempted to eat it. I don't know. Okay. This is an example of what an IR spectrum looks like. Okay. So percent transmittance is basically how much light's been able to go, how much light kind of went through and interacted with the sample. And so we can see their percent transmittance. We can also have percent absorbance, and depending upon which option is chosen, your y-axis looks different. If you choose percent absorbance, basically you end up inverting the spectrum, and it looks like you have peaks instead of, we still call them peaks, but these are really dips, right, that we're looking at here. So to me, the IR spectrum always looks like stalactites in caves that are hanging down from the ceiling. And that's the stuff that we're interested in. So I don't really care. That looks like a peak because that's up top, but that's not really important, Ryan. Yeah, so like this group is a peak, this group is a peak, even though it's inverted, that's the stretching for a certain functional group. Yeah. So we don't get a nice flat baseline for this that peaks rise out of. Instead, we have stretches that dip downwards from an upper position. Okay. If you are looking in the slides, there's definitely some math on how to calculate some of these things. Now, we never have to calculate these wave numbers, but I will use this slide as an opportunity to point out what the x-axis is. It is wave number, which is inverse centimeters, okay? So you can call it wave numbers, or you can call it inverse centimeters. That is the unit. So whenever you're reporting your stretching, a lot of times your stretching will be in a range similar to our melting point, okay? But you have to use those units of centimeter to the -1, okay? And of course, here we've got kind of that calculation. It's looking at the frequency of light that the detector is getting out, or the frequency of energy that the detector is detecting, divided by the speed of light. Okay. So when you are trying to analyze an IR spectrum, you got to look at 3 different things. The wave number, so where is it located, right? This kind of first peak on the right is located around 34, 3,300, okay, wave numbers. You got to look at the intensity. These two peaks and the 3000s are a lot bigger than our peaks that are over around 1,000. And then you have the shape, okay? So this peak at 3,500, 3,400 is pretty broad in comparison to, say, this peak that's right there around 800 or 900. So we've got three different things to look at. Here, basically, they're telling us what the wave number helps represent. So the wave number for that stretching vibration depends upon how strong the bond is and the masses or the mass numbers of the atoms that are involved in that bond. Okay, again, we're never going to have to calculate this based on masses or anything like that, but that's why we get different wave numbers for different functional groups. Okay. So the next slide keeps that equation, but also gives us an idea of our different functional groups and what ranges they might show up in. CH, for instance, shows up around 3,000. We now know what D means, right? Deuterium. So CD, it makes sense that it would show up similarly, but it does have a different mass number. So it's 2,200. Carbon oxygen, we see it at a different place. And we see differences in triple bonds versus double bonds versus single bonds in the bottom, right? Carbon nitrogen, the cyano group that, let's be honest, a lot of us struggled with on the test, shows up around 2,200. CN double bond shows up around 1,600, and CN single bond shows up around 1,100. So we're going to see lots of tables for these stretches. They are prevalent. You can Google IR table and you're going to be able to come up with something off the internet. I think on Moodle, I have at least 2 embedded outside of our slides. Number one, this is not you eventually kind of get a feel for some of the functional groups. I wouldn't ever say that you really have to memorize them, but you'll need enough practice to kind of feel comfortable with some of the really major functional groups. This is a very vague table, in my opinion, because it's really looking at the spectrum and then showing you where the different functional groups come. So anything that's bonded to H tends to show up at higher wave numbers. That is an X, which is slightly unfortunate. That does not necessarily mean halogens. That could mean carbon, like we saw on the last slide. Your triple bonds are showing up in a pretty tight range, 2,300 to 21. Double bonds are showing up 1,850 to 1,650, something like that. And then single bonds are down on the smaller number end of the spectrum. Okay. So we've got some terms for this. The single bond area, these smaller numbers are called the fingerprint region. And a lot of times they don't get analyzed in IR spectroscopy. You can, and occasionally we may have to go look for a specific peak in the fingerprint region, but usually you want to use this diagnostic region because that's where the major functional groups are. That's where you've got that XH, that could be OH for an alcohol or a carboxylic acid. Over here, you've got your cyano group or your alkyne. You've got your alkene. That could be a carbonyl, indicating that you have a carboxylic acid or a ketone or aldehyde. And then you've got your carbon nitrogen triple bond. So for the most part, you want to look in the diagnostic region first and figure out what major functional groups you have. Then if you're still not sure if you made your product, go and look in the fingerprint region, okay? Fingerprint region is really good if you need to know something specific about like some nitrogen bonds and some things like that. I've seen a few people use that. Okay, so here's an example of an IR spectrum of butanol, 2-butanol, okay? Notice we've got definitely some peaks in our fingerprint region. We've got this big alcohol functional group, and I knew that was there because we see this peak right here. And we're going to talk about peak shape next, but this is about where your alcohol peak comes off. And then this less broad peak is going to be your carbon hydrogen peak. So that's butanol, 2-butanol. Here's propanol, 2-propanol. So there is a difference in what these two look like. You can still identify the functional group pretty quickly. The carbon, the oxygen hydrogen and then the carbon hydrogen. But that fingerprint region does change because you have fewer carbon hydrogen bonds, and fewer carbon carbon bonds would really be what we're seeing down in the fingerprint region. And there, I've got them stacked up. I went ahead and stacked them so you can kind of see the comparison. They are pretty similar, but the intensity has kind of changed, and some of the pattern has changed down in the 2-propanol. Okay, let's see. So, I tend to think of the IR spectrum based on functional groups, but you can look at it based on the hybridization of certain carbons. So, and we saw that the way that they had that last kind of spectrum divided up. They had where the triple bonds were, where the double bonds were, and where the single bonds were for carbon. So we see here again, sp3 hybridized carbons tend to show up in that, if they're bonded to a hydrogen, tend to show up around 3,000. Your carbon hydrogen, when the carbon is sp2 hybridized, shows up around 3,100. And then if you have a triple bond, that carbon hydrogen, you end up seeing basically the more hybridized the carbon is, or maybe the less hybridized, you see higher wave numbers. Any questions? To me, this kind of phenomenon is useful, but on a surface level, the functional groups are the most important thing. And then you can go back and dig for more information like this in a table when you need it, as opposed to focusing on remembering this trend about hybridization and all of that, okay? So here's what that can look like. So here's our CH in the sp3 hybridized carbon in that first IR. We see at a higher number, even further down, the double bond. So this would kind of be a good indication that, oh, this has a double bond in it, but we also have sp3 hybridized carbons. And then we see the triple bond really moving away from where the CH peak typically is shown. Okay, let's see. All right, resonance, that we have come to realize does not leave us, impacts the wave numbers for these different functional groups, okay? So we've got a nice example with our ketone here. They're reminding us of what our resonance structures look like. And they've told us that for this particular ketone, you have a wave number of 1720 for that stretch, okay? If we look at the next slide, we start seeing, here's our original molecule, right? Just the ketone. Here's a conjugated ketone, and we know the ketone itself has resonance, but now we also know that the double bond that's just down the row from it, just down the molecule from it, can play into that as well. So this further stabilizes that, and we see it lowering the wave number for that, okay? Here we've got your ketone, but now it's attached to an OR group. We know that the oxygen can contribute into that resonance, and we get a different resonance pattern, 1740 for that stretch. And then when we have the ester plus a conjugated pi bond, we see a lowering effect as well. Again, this is something that it's nice to kind of be told that these things can influence it, so that when you get a certain molecule next semester and you can't quite figure out where something is, you can go back and delve deeper. But unless you're using IR a ton, nobody would expect you to really remember some of these values or anything like that, okay? Just kind of the general idea that, oh yes, this does this. This helps stabilize and lower the wave number, something like that. Okay, signal strength. Signal strength, the longer the peak, okay, the stronger it is. Pretty straightforward, okay? So they're going to kind of explain why that's the case and how we can use that to our benefit when we're analyzing them. We've got a little bit of dipole information, okay? Here's what's going on with those dipole moments. They're creating electrical fields surrounding the bonds, and so you get that wave nature, okay, of energy and electricity, okay? And now we've got two different double bonds right there, okay? One of them is a polar double bond, one of them is non-polar, right? And we see the difference in that wave nature. So that ketone double bond sends out a much bigger signal than just the alkene double bond, okay? The greater the bond polarity, the stronger the IR signal, the longer the peak is. So if you think back to some of the IRs that we've seen, that peak that I told y'all that was OH, that was a really long peak. And that's because that's a polar bond. Here's another example. This would be a compound that has some kind of alkene functionality plus a ketone. And we see here our, they've clearly just snipped out little bits, but our ketone has a much longer peak because of the stronger signal than the alkene peak. Any questions? Okay, let's see. Okay, stronger signals also exist when you have multiple bonds that are the same, that have the same type of vibration. So if you have lots of alcohol groups on your molecule, the alcohol group is going to be really big. If you have lots of CHs, the CH peak is going to be really big. It's not necessarily capable of giving a different signal for each one of those OHs, even though the environments might be slightly different, okay? Yeah. Signal shape, the last thing we gotta think about with respect to looking at the IR and what that could mean. We've got on this slide an example of broad signal and narrow signal, and it's really self-explanatory in terms of what the picture looks like, okay? A lot of times our alcohol stretches will be really broad. There's certain situations where they won't be, and we're going to talk about that. But OHs tend to be broad, whereas other functional groups tend to be narrower. And that probably gave us a bit of a hint about why that's the case. We know our alcohol groups are capable of hydrogen bonding, and that's exactly why we see this different shape for the signal with these alcohol bonds. So when you have an OH bond that is involved in hydrogen bonding with another molecule or with itself, if the molecule is big enough, then you're weakening that bond in between, the covalent bond between the oxygen and hydrogen, because the hydrogen is being pulled towards the other molecule a little bit, okay? And so what we see is a broadening. If you have that kind of slightly weaker association between the covalent bond, you end up broadening the signal for that particular OH vibration as compared to an alcohol that is not involved in hydrogen bonding. So sometimes we've seen illustrations where we just had one peak for OH, and then we had our CH peaks right behind that around 3000. In this particular molecule, we have two peaks for OH. We have the really broad one that is very easy to identify. When you're looking at a spectrum, you should be able to say, oh, for sure, this has an alcohol, or no, it doesn't. It's really obvious because there's that nice broad. But if you see this little peak behind it, that's usually indicative that some of the alcohols aren't involved in hydrogen bonding. It's not a different functional group, even though it is a separate peak. It's just one that's not involved in hydrogen bonding. So here we're looking at a carboxylic acid. We see our really broad, and see what I mean? Like, it's so obvious that you have a really broad peak right there. Nothing else broadens quite like an OH peak. And so I immediately look at this and say, hey, that's an OH. And then I'm looking further into my diagnostic region, and I see this stretch around 1700, okay? And 1700 is your carbonyl stretch, your carbon-oxygen double bond around that. And so that's a good indication to me that we have a carboxylic acid. Okay, this is just the carboxylic acid. Let's see. Yeah, so our carboxylic acid, this OH peak is kind of stretched over a little bit. We see it coming out more around 3000. If we go back a slide, this OH peak was coming out around 3500, 3400. So part of the reason we see that in our carboxylic acids, we see that shift. We know it's still an alcohol stretch because it's so broad, but part of the reason that it has shifted down is because your carboxylic acids are forming through hydrogen bonding these kind of dimers. So two molecules that are kind of locked together through interactions, but non-covalent interactions. So, you know, we've got one carboxylic acid turn one way and one carboxylic acid turn another here. Okay, let's see. I have no idea. With our amines, that functional group, we see primary and secondary amines exhibiting stretching, but we don't really observe anything for tertiary. And that's because tertiary amines, we haven't gotten to this classification yet, but it's not a far leap to go from tertiary carbocations to tertiary amines are attached to 3 R groups. There's no hydrogens attached to those nitrogens, okay? So we've got examples of IR signals for a primary amine that's on the left, and then at least I can figure it out. And then on the right, we have our secondary amine in piperidine. So we see here that amine, that NH2, is actually represented in the IR spectrum by 2 peaks. Even though that's one functional group, it's because there's 2 hydrogens attached to that one nitrogen, and they exhibit slightly different vibrations, okay? And then we see when we go to the secondary amine, there's only 1 hydrogen attached, and so you see 1 peak. And then it makes sense now, if you know there's no hydrogens on a tertiary, that you would see no peaks for that. So IR is useful. It's a great spot check. It's great. It's fast. But there's certainly some functional groups that you can't really get information about out of IR. Okay, so we know that there's different kinds of stretching. We've got symmetric stretching where the same thing, like both of your atoms are moving at the same time in opposite directions. And then you have asymmetric where one's coming in, one's going out, back and forth, okay? That is actually what's causing the two hydrogens to look like 2 different peaks. It's actually that consequence of the 2 different types of vibrations that the hydrogens can exhibit with respect to one another, okay? Because you can picture the middle atom is the nitrogen, and now you have a hydrogen and a hydrogen out on the end, and they're vibrating in different ways. But the trend still looks like when you have a primary amine, you have a peak for each hydrogen to keep that in the forefront. It's not because it's 2 different hydrogens, it's really the stretching, but it still works to remember it that way as well. We're getting serenaded with happy birthday here if you're in person. That's exciting. Okay, so when you're trying to analyze an IR, we've looked at the 3 things that we've got to pay attention to. And once again, just like today in class, when we were talking about our substitution versus elimination, we've got to do it in an order in order to kind of not really drive ourselves crazy and think about too many things at once. So the first thing you always want to do is focus on that diagnostic region, okay? And here on this slide, we've got our reminders for where double bonds show up, where triple bonds show up, where our hydrogen covalent bonds show up. Okay, so that doesn't necessarily have to be XHX for halogen. And of course, we need to look at our wave numbers and intensity and shape. So here we're kind of looking at only the diagnostic region of the spectrum. There's more spectrum over to the right that they've cut off for us. And they have shown where the different functional groups should show up. And of course, this spectrum doesn't have anything where an alcohol group would show up or where an amine group would show up, where an alkyne, a terminal alkyne that has a hydrogen on it would show up, or where an alkene with a hydrogen would show up. But it does have the CH peak with the sp3 hybridized carbon. So if I was looking at this, I would immediately know that we don't have any kind of alcohol, carboxylic acid. Really, we don't have much in the way of interesting functional groups. Maybe there's a ketone. They haven't showed us much for that yet, but it's kind of looking like maybe it's just an alkane or something. So next semester, we will do IR on a lot of our products that we make, okay? To confirm that we have made a functional group, to confirm that we have changed a functional group from the starting material to the final products. In which case, it's useful to take an IR of your starting material to compare with your final products, especially if you're going to put it in a lab report, for instance. Here is a reaction, and we actually do the reverse of this next semester. But we're going from an alcohol to a carbonyl. That's called an oxidation. We're increasing number of bonds to oxygen. It does relate back to that lovely Gen Chem concept of oxidation numbers. But we've got an OH versus a carbonyl. Hopefully at this point, even though this is kind of new, you can start to visualize how this might look different in an IR. You know, this starting material should have that really broad alcohol peak around 3,400, and we should not see that at all in our final product. If you do, your reaction wasn't complete. You still have impurities. Maybe you need to go back and repurify. Likewise, our starting material shouldn't have any ketone in it whatsoever. Otherwise, you should complain to your supplier, right? So your carbonyl stretch, which is around 1,700, shouldn't be there. And then you should distinctly see that show up in your product. So you can use this as a really nice spot check for, oh, hey, I'm missing this functional group that was there to begin with. Yes, green light, my reaction at least looks like it did the right thing. It at least got rid of the functional group we wanted it to. Okay, here's another example. We haven't quite gotten to some of these reactions. Some of them I think we'll get to this semester. But, so we've got a ketone right here. Or not a ketone, sorry guys, an alkene right here. And we're looking to create this next alkene. Those two IRs would look pretty similar to one another, wouldn't they? So another thing that we can do, and this is a reaction that we'll learn about a little bit later. So this is actually step one, fun fact, is an addition reaction that I think we'll get to before the end of the semester. Step two might look familiar because it's an elimination. Okay, because we've got that ethoxide right there to give us a new alkene. Since those two products look really similar on the IR, if that's the only way we have to tease out whether we have the right product, we can do something called ozonolysis, and that basically cuts your double bond in half. When you do that, now we've got two different ketones, and we can kind of compare those a little bit. These two ketones would look very different from, say, the two ketones if you hadn't done the reaction. So there's still ways, even if your starting material looks very similar to your final product, you can do a kind of diagnostic reaction and run an IR to kind of verify that, yes, you got the product. You made the final product. If there is a literal 1 and a literal 2, then it's step 1 and step 2. If you do not have a 1 and a 2, which we have not seen yet, what we have seen is, say, your ethoxide and then ethanol as a solvent. A lot of times solvents will be written underneath the arrow because it's useful information, or they're going to react with something like solvolysis that we've been talking about for the last couple days. So you need that there, but it's not reacting in a separate step. Literally, this is one mechanism and this is another mechanism. And sometimes you actually work the product up in between those two steps. So there's a purification step in between those, but for squishing your reaction information into one place, you just put them step 1, step 2. Did you have a question, Ryan? Okay. Does anybody online have a question? That's actually the end of the slides. So hopefully, I think the IR spectra that I have up in Moodle are from a textbook. It is definitely not our 3rd edition. So the 3rd edition might have it illustrated a little differently. And then I have 1 or 2 that I've pulled offline somewhere. And honestly, people have gone to town in terms of illustrating these. Sometimes they use color coding. Sometimes they do other things. Sometimes it's honest to God list of table as opposed to a spectrum that they've kind of put functional groups. And so you can get, out of the list of tables, you can get much more information like the asymmetric versus the symmetric stretching, and be able to find out which hydrogen's doing what in the nitrogen and all that kind of stuff. But you can look at the different things, the different tables, and look and see which one you kind of like best. I'm pretty sure that information shows back up 2nd semester in our lab. But you've got to feel at least vaguely comfortable with this concept and running an IR for the lab final and the lab final technique check. So if you have any questions, think about it. If you don't have questions now, that's fine, but absorb it. If you did not need that makeup lab, you didn't have to do this, but I did put a worksheet up. That's what we always do for the IR lab. There's a worksheet where I have given y'all molecular formulas and then IR spectrum, and then you have to build what the molecule looks like. Or I have 2 or 3 molecules and you have to match it up with the spectrum. That's kind of the level of being able to identify things from this set of slides in this lab. So take a look at that. You don't necessarily have to work it, but it might behoove you to look at it to get a feel for how problems could be asked. And the other reason I wanted to do this can show up on the ACS exam. I don't know what those questions are. I won't until sometime in November. They're not emailing them to us. So I have no idea if IR is on there or not. I know usually there's some spectroscopy on the 2-semester final exam. I would assume there will be some spectroscopy on the 1 semester. All right, we're good to go. Have a good night, guys. They can't see me.